Hi, my name is Jordan Hall, and thank you for watching my talk at the Research and Creative Activities Symposium at CU Denver for 2020. The title of my talk is Derivative-Free Optimization and Active Subspaces in Inverse Problem Theory. In an overview of my talk, I'll give a brief background on uncertainty quantification, and then I'll jump straight to an application of modeling COVID-19 cases in Denver. And then finally, I'll quickly talk about some of my active research and how that connects to number 2. Okay, so some notation. We're going to have a parameter space, capital lambda, and a data space script D, and a map between those two spaces, capital Q. And we can denote observations of the data modeled by evaluations of Q at some parameter, little lambda, in the space of parameters with D equals to Q of lambda. And just a note that we describe uncertainty in UQ with densities, or in other words, statistical distributions. You might be familiar with normal distributions, or these are actually 5 different order statistics. So just we might have different distributions assumed on parameters. We'll map those through Q and obtain different distributions in our data space. And that's exactly the UQ problem I'd like us to consider here. So given an initial description of uncertainty in our parameter space in our model, can we predict uncertainty in the data space? This is called a forward problem, and the solution of that is called a push forward. Now, let's get straight to our application. Now, here's the confirmed number of cases of COVID-19 in Denver that is up to date until yesterday as of this recording. And you can see that we've reached nearly 2,500 confirmed cases. I also want to point out that I think we're all aware that the cases exhibit exponential growth in this early time machine. Okay. Now, how do we model exponential growth? Here's a model, and I'll continue to use our notation of capital Q. Exponential growth is usually modeled using some assumption about the initial number of confirmed cases in the population, the time, and here we're going to use days, and a doubling time. So how long does it take for that population of confirmed cases to double in the population? And that's also going to be in the unit of days. So for fixed values of I naught, and that's the number of cases initially, and the doubling time, we can use shorthand to evaluate Q of I naught, T, and T double all at some point in time, and we can call that N of T as well, which we might use on our plots for shorthand, just as a note. So initially, let's consider the following uncertainty on the initial number of cases and on the doubling time. So for the initial number of cases, let's assume that they're normally distributed with a mean around 2 and a very small variance. And this is in line with the data. There were 2 cases initially in Denver that we observed, and I think we can be fairly confident about that, although that data has been updated day to day. As well, the doubling time will take to be a mean around 6 with a variance that's larger than the variance that we're using for the initial population of confirmed cases. And that's because the doubling time is a little bit more uncertain, and it's also changing over time, which we'll discuss in a moment. So the forward problem that we're going to consider in this application is to characterize uncertainty in a future prediction that depends on uncertain values of the initial number of confirmed cases and the doubling time. So in other words, how does uncertainty propagate through our map, depending on the uncertainty in our parameters? That's kind of an initial question that we're going to ask ourselves here. And here's how we can solve this kind of a question. We can just sample different values of the initial population and of the doubling time, and we can just plot the different curves that we obtain, and we can do this over and over. And that's what we've done here. I drew 100 samples of pairs that were drawn from the distributions I described a few slides prior. And I plotted all of those curves. And just a note, it's very standard to apply a logarithm, and what you obtain is actually a linear function when you apply a logarithm, and I'll leave it to the viewer to verify that fact. But a natural question here, are we even predicting our data? And sure enough, what we're going to see is that more or less we're predicting our data within the more current time regime here. Okay, so here I've plotted all of the logarithmically scaled curves that we observed earlier. But now I'm also plotting the logarithmically scaled Denver data as well. And what you can see is that the data falls within our predictions, especially within the most recent time frame here, where our model kind of fails to predict the early cases, but it's becoming more accurate. And a lot of that has to do with the doubling time. Notice how there's a certain slope that we have up until about the 25-day mark, and then all of a sudden the slope of this line seems to kind of break or change a little. Well, time to make an important note. Policy decisions are affecting T-double in real time. So right around the 25-day mark in Denver was a few days after Mayor Hancock had issued a stay-at-home order, which certainly would change the doubling time as long as people were following it, which I think after a couple days people really were. A second follow-up question to get more specifically at a prediction is to characterize the uncertainty in a future prediction depending on those uncertainties in the initial parameters that we were just looking at. And this time I think we should choose more precise predictions, and or rather we'll choose more precise initial densities, and then we'll obtain more precise predictions by doing so. So by choosing a smaller variance in both cases for the initial population and for the doubling time, we will obtain more precise models and therefore more precise predictions as well. But I'm also going to choose a slightly more pessimistic doubling time. The smaller the doubling time, kind of the worse. Before our mean was 6 and now our mean is 5, so the doubling time is slightly faster, meaning the growth rate will be a little bit more in the population. How do you solve this forward problem? We'll still draw a bunch of samples of I naught and T double, but this time I'm going to store some specific values of the actual map evaluated at a future prediction of T star, which is going to be 56 days. That's actually the end of April. So that's a prediction for a couple of days into the future from now. And we'll repeat this over and over again, and then we're actually going to approximate statistically the density of these predictions using what's called kernel density estimation, or KDE, which is a really important tool in UQ. So it's really familiar plot again, where you can see instead of having a more spread out kind of band of red lines, they're a lot more tight because of the precision that I've chosen here. And also there's a lot more of them. Now I'm sampling 20,000 different pairs, plotting all of those different models. And now the data kind of falls, especially within this time regime, really nicely in the middle of those predictions. So now, a little bit into the future, at time equals 56 minutes, I need to make 20,000 predictions and come up with statistics about that. And that's exactly what I've done on this slide here. So now I have used KDE to approximate the density of our prediction for the end of April. And what you find is that the mean of this density is very close to 5,000 cases that we could have. But just keep in mind that the mean is not the prediction, right? The prediction or the answer to a forward problem is the density. Okay, so there can be a little bit of an issue in just interpreting the number, the mean itself. Really what we want to interpret is, or maybe certain intervals, right? Like this interval that's kind of banded here in black that contains 85% of predictions, which basically says with this model, with our assumptions, 85% of the time, the cases by the end of April would fall within this band. So sometimes it might fall well below the mean, sometimes it might fall above. and it depends on factors like social distancing. So to finish the talk, uh, I'll just kind of say a little bit about my research. So inverse problems ask a slightly different question. They ask you to update your description of uncertainty in the parameter space given everything we've already been working with. And there's a way to do data consistent inversion. And this is pioneered by Dr. Troy Butler, who's here at CU Denver, and he's one of my co-advisors on my PhD advisory committee. And DCI basically ensures that when you solve a forward problem for your updated density, it will match your data perfectly. So you get this nice overlap here. There's actually two curves being plotted, but they're both overlapping very nicely because of the properties of DCI. And finally, just a couple of notes that if your map can permit dimension reduction, and if you also don't have access to your analytic gradient, then in some cases, you can actually still perform DCI using deterministic optimization. And my advisor and I, Dr. Varas-Carey, have modified a DFO algorithm called STARS to perform in the active subspace and act a little bit faster in those cases, which you see here with the red curve that is more optimized in that space. Here are my literature references, and here's my data and media reporting references. Thank you for watching my talk.